Alright, we have two more identities we're going to try to prove, and I will say they are the two toughest, but some things to look at. Here, when we're trying to prove this identity, I say always start on the more complicated side first, and I would say in all of the other problems, the left side's been the more complicated. Here, this right-hand side looks to be more complicated because it's a fraction, and fractions are usually easier to simplify. Here, in this case, how am I going to simplify it is a little tricky. But I say, well, the bottom is definitely, it has an easy conjugate. And that's one of our strategies, is sometimes you're going to look to multiply by the conjugate. So if I do that correctly with parentheses, the top is going to be cosine 1 plus sine x. And the bottom is going to be, that's an easy conjugate to multiply, it's 1 minus sine squared x. And when I get to that, I say, well, now I've got a 1, I've got a sine squared. This could be a Pythagorean identity. So when I look at this bottom piece right here, I think, oh yeah, I know sine squared x plus cosine squared x equals 1. And if I was to subtract sine squared to both sides, all right, I'm left with cosine squared x equals 1 minus sine squared. And that's going to be the substitution I'm going to make to start. So on the top, I would have cosine, missed out an x there, cosine x, parentheses, 1 plus sine x. On the bottom, we already figured out that whole bottom is equal to cosine squared x. And now I look to simplify a little bit further. I say, all right, well, cosine over cosine cancels out. And now I'm left with 1 plus sine x over cosine. And I got to figure out, how does 1 plus sine x over cosine, how is that going to simplify to secant x plus tangent x? And it has to deal with our rules of division. I could take this cosine and divide it into each of these individually, meaning I could break it up into two division problems, make it two fractions. Think of it as the reverse of adding a fraction, right? Usually you have common denominators and you can combine it to one fraction. You can think of this as, I had the denominator in both, and I'm going to make it two fractions with the same denominator. Right. Well, I know by our reciprocal identities, 1 over cosine is the same as secant x, and I know sine over cosine is tangent x, and now I have arrived at the secant x plus tangent x that we were looking for. Alright, last one and trickiest one. I will say this is the trickiest one because both of these sides are relatively complicated. And the way we're going to solve this is we're actually going to need to simplify both sides just a little. Okay? So let's focus on trying to simplify the left-hand side. If I try to simplify the left-hand side, I know cotangent squared can be written as 1 minus cosecant squared. I'm sorry, cosecant squared minus 1. By our Pythagorean identities, cotangent squared theta is equal to cosecant squared theta minus 1. So that's the first piece I'm going to be using. I'm going to substitute the top. Cosecant squared theta minus 1 over 1 plus cosecant. That hasn't done me a lot of good, but I noticed the top is now factorable. That's two terms. Those two terms are factorable. I could factor it as a difference of squares. And if I factor it, it becomes cosecant theta plus 1 and cosecant theta minus 1. And the nice part about that is the bottom, if I just change the order, I should notice something cancels out. Boom, boom, both of those have canceled out. So I've simplified this left-hand side down to cosecant theta minus 1. Let's see if we could do something similar on the right-hand side. So now focusing on the right-hand side, I've got to take this statement 1 minus sine theta over sine, and I'm actually going to use the trick we used on the very last slide. I'm going to divide this sine into both fractions. Right? And when I do that, I get 1 over sine minus sine over sine. Well, we know sine over sine. Sine over sine is 1. And but anyway, 1 over sine is cosecant. minus 1. And now I have proven that these two sides are both equal to cosecant theta minus 1, so both two sides are equal. But if you noticed, I did not work on both sides at the same time. I worked exclusively on the left and exclusively on the right. If you try to do operations to both sides, you are going to run into problems. It's by far the most common mistake I see on any of these proofs. Try to work just on one side. If you notice, in this entire notes, I never said do something to both sides. It's always been work and simplify one side. By factoring, by multiplying by the conjugate, by simplifying like this little division trick. There's plenty of methods, and as you work on them, you will hopefully see them a little bit easier. Good luck.